Hello everyone, this is machine learning. Today in our 13th lecture, we're going to look at recurrent neural networks. And just a quick recap. So remember we looked at confidence and how confidence can be used to, take in high dimensional data, for example, images, and predict abstract labels, like, for example, whether it's a dog or a cat, or whether other objects are, to be found in this image. And we have seen how confidence and especially deep confidence kind of build up a hierarchy of low-level, mid-level, and high-level patterns that they are able to detect. So, for example, here in this image example, our lowest level are the pixels, right? So these are the input variables, and by applying kernels that we convolve the image with, we can detect low-level patterns. And these patterns are those that the network learns to detect to be able to, improve the prediction accuracy, for example. And this hierarchy then, of course, shows increasingly abstract concepts. For example, we could be detecting gradients or like texture types or different geometrical shapes, or if you combine these object parts, let's say like eyes and noses, or dollar bills. And in the end, we then of course come to the output labels, which are on the top layer of this hierarchy. So as I said, deep networks, confidence like ResNet here, can be trained to predict this low dimensional label vector from high dimensional images. And each of these layers contain activations that kind of represent this hierarchy of objects. Now, what about sequential data? So, imagine we had this patient with like 20 electrodes on his head, and we would record potentials over time. And we wanted to train a model that predicts what kind of thoughts this patient would have. Although, I mean, this is probably nothing realistic here. But anyway, this model would have to detect patterns, low level, mid level, and high level, in these time series, right? So a long time. Another example is machine translation. When you had a sequence of text as an input, for example, here in Greek, and you wanted to translate this into English. Patterns here in the sequential data now, make up words or, parts of sentences and sentences. And obviously these have to be detected to be able to actually, translate them. Similar example is speech recognition, when we have raw audio data as an input, and the model now should detect, how, basically this membrane in the microphone vibrated to detect, phonemes and words and in all these things. And since the world, is really what it is, so like a dynamical system, it's not hard to find examples of sequences, recordings that live in time, for example, that could be subjected to a network that then, accomplishes a task, like here, video captioning an input is a video and an output is a description of the scene. But also images or other static data can be read in a sequential manner, right? For example, think of a sub window that you scan in always the same kind of fashion over this static image, and therefore you create a sequence. And the question now, and for the remainder of the lecture is, okay, so how can we learn these patterns in time or along the sequence? And these ideas are really not that new. So Minsky and Papert in this 1969 paper on perceptrons and those many variations introduced the notion of multilayer perceptrons with loops. And although back in the day we didn't even know how to train deep perceptrons or multilayer perceptrons, but these ideas, and I really recommend this read, we'll share the link in the description. The idea was there, and many other ideas were already there. And it's so cool to see that it sometimes takes 50 years or more to actually make them work. Okay, but so the actual, I think, first formulation of what we'll see in the first part of the lecture was proposed by Rumelhart et al. In this famous paper that proposed backpropagation for networks and also introduced recurrent networks and how to train these, although they had loops. And in the remainder of the lecture today, I'm going to show you a type of recurrent network that's called long short-term memory, or LSTM. And Anton Hochreiter and colleagues in the late 1990s proposed this, and people still use it today, although the popularity of recurrent networks has kind of declined, but still I think it's a very important concept, and you have to know this, and that's why it's in this lecture. So in the vanilla formulation of recurrent neural networks, we have basically this loop connecting the output of the network and its input, right? So usually we use H to denote a vector that's called hidden state. That's basically holding, all the history of inputs. And, as usual, we have X and Y as inputs and outputs. The output Y now can be seen as an element of a sequence as well, but this is basically just mapped with a linear layer, right? So the hidden layer H, also with time index T, now is just multiplied with this matrix W, H, Y, so mapping from H to Y. You'll see differences in how the output is obtained from the hidden state, but this is the most simple way to do that. And the hidden state itself, like we said, at time t is obtained from, well, two multiplications. So one, the input x at time t is multiplied by, again, a matrix, so a linear mapping of input to hidden state, and also the hidden state is mapped to itself from the last to the current time. You see this sometimes in this concatenated kind of way. So the input vector is composed of part the actual input xt and the previous hidden state ht minus 1, and everything is then put through this 10h, through this one nonlinearity. 10h is a sigmoid shaped function between -1 and 1. You should also be able to to draw that in the final maybe. So again, the input to the network, to its only nonlinearity, is both current information, so current meaning the current time step, or the index, the current index in the sequence, and old information, historic information, represented by age. And age isn't just the previous time steps information. Age contains all time steps up to t-1 or t. These matrices, WHY, WXH, and WHH, so exactly these transition mappings, these are the only parameters of the system. And you may ask yourself now, so how can that be powerful, right? So there's just a handful of matrices here and just one nonlinearity. How can that be powerful? And how do we train these how do we optimize these three matrices in the first place? And the first concept for you to understand how this works is unrolling or unfolding the recurrent network, right? So a recurrent network can be seen as, well, let's say an unlimited sequence of feed-forward networks. Obviously we don't have unlimited memory, but this will be the way we train this. So this network with the loop can be seen as a network of inputs, hidden states, and outputs in time, that lives through time, or lives through the progression of a sequence. So those matrices here can be used to map X to H and H to Y, and also H to H in the next step, using the current input producing the current output. And we can continue this process, this unrolling, until we reach a predefined length of our sequence. And by doing that, we have produced a feed-forward network, a well-defined mapping of inputs to outputs with no loops anymore. And please note that each of these transitions, right, so from H to H, or from H0 to H1, and so on, they're all using the same matrix. All hidden state to output mappings are using the same matrix, WHY, and all input to hidden mappings are using the same matrix. Okay, but this somehow also explains how this can be powerful, right? It's because an input X0, for example, has influence on the output at Y4, for example. And there are 1, 2, 3, 4 nonlinearities involved, and we can think of like a 4-layered feed-forward network. So, but now this basically explains how you train this. So by unrolling the network, you have a feed-forward network that you can just use or with backprop, like we already introduced you to, right? So this is called backpropagation through time, and we'll go through an example in the following slides. And this example is a character level, a language model, right? So our goal is to come up with an RNN that can be used to generate text. So it's a model of text, and we probably have a big data set, maybe a couple of machine learning books, and we take characters, and the RNN is supposed to predict the subsequent character. Could be letters, could be spaces, could be commas and periods and all these things. So once this is trained, and I'll show you in a second how this works, once this is trained, we could, for example, use this as a generative model. So we feed it in an H, and it produces an E, and we'll take that prediction and put it back into the same network to produce an L, and so forth, so that we end up with maybe the word hello. And look at this part. So an L may produce an L, but also depending on what the hidden state was, is able to produce an O, although the input was the same. So how do we actually train this? Okay, so let's do this step by step. Let's start by unrolling the network for the first step. And as you know, from how to train forward networks, we need the definition of a loss function. So L somehow compares the actual output y0 to the label, which was the letter or the character E. Now, so we'll then backprop the gradient of this loss into these matrices. But before we continue explaining, how this works and what differences there are to training feed-forward networks, good. So to train this, let's just unroll the network for one time step. So this then gives you basically a very simple feed-forward network. And you know that we need to define a loss function. So how do we compare the output y to the label? So in this case, the letter E. And before we go into detail, about how to backprop this into the weight matrices, we need to ask how do we represent the input and the outputs, and also ask what kind of loss function can we use. How are letters or characters usually encoded in the computer? Well, we use some kind of character encoding, right? ASCII or UTF and all these things. But these are single numbers, and we usually don't use single numbers. We use one of two alternatives, and the most simple, let's say, the simplest way to do that is encoding letters with a single one in a zero, otherwise zero vector. So count your vocabulary. How many different characters do you have? So in our example, it's 4, right? So HELNO. And assign a 1 to the ith dimension for the ith character in the vocabulary. So this would then give you this kind of encoding, and this is called one-hot encoding, or these are one-hot vectors because one element in this vector is hot. But this is not very efficient. So if you have a huge vocabulary with many different characters, you usually use something else, which is basically selecting with this one-hot vector the ith column of this of this matrix W, and these are called embeddings, right? So word or character embeddings are lower dimensional vectors than these one-hot encodings. And the advantage of this approach is so we can backprop into these matrices. So the network learns codes for characters that are in agreement with our objective, right? So if, for example, the loss can be minimized further by rearranging the position of where L's and H's and E's and O's are, then the network will find these positions. So assuming one-hot encoded inputs and outputs, which also means one-hot encoded labels, we will probably have outputs like this. So each of these numbers represents, not the probability yet, right? Because the sum of these values isn't 1, and also we have negative values, and that's not possible with probabilities, but we call these raw values logits, yeah? Because in the next step, and I haven't shown you that, but we have to cover this also, we push this through another nonlinearity, which is called softmax. And so this layer basically takes in the output vector of logits O, and for the ith element, it puts these in an exponential function and normalizes this by the sum of each of these exponential values. Yeah? So the sum of this vector y hat here will then be 1. Yes. So I did this here for the values that I've shown you previously, and you see that the most probable character here is the second one, and the others, being reduced due to this exponential function here to only marginal probabilities. I mean marginal in their magnitude, and the loss function that we commonly use in these kinds of problems is cross entropy, because we are basically classifying, right? So this is a character classifier. Okay, now let's have a look how these things are trained. So remember, we wanted to unroll this network, and I've did this for 2 time steps now, and you see that we have 2 gradient like sources. So first comparing the first character to the label, and then the second one as well. And of course, we can do this for many, many more. But you see how now the gradient information and the learning signal can enter the network from different positions in the graph. And so continuing this until the end of our example here, I wanted to show you what this means in terms of gradient updates. So, and let's start from the back. So the last character, for example, is compared to the label, and then we can backprop this into these matrices. And always remember that these arrows here represent mappings represented by matrices that are the same matrices here. Yeah? So we have different values for those hidden states, for example, but the mappings are always done using the same matrices, right? And now we want to compute the gradient updates for these matrices. Now, so we can backprop this into here, but we can also go back in time, right? So we can backprop this through this one matrix multiplication of H2 to H3. And of course, we can go back all the way to our first character. And now, gradient information kind of could come in. Let's just look at this matrix here, at this input to hidden state mapping. We can receive gradient information from this channel, and from all the other channels. Yeah? And in the end, we have 4 different gradient updates that we have to integrate, like summing up or averaging. Okay? Okay, so we will train these networks in the assignments. And before we move on in the lecture to see what kind of other networks can we think of and can we train, I wanted to share with you this beautiful blog post. So Andre Karpathy is the author, and he is chief AI or director of AI, whatever, at Tesla. And so he wrote this blog post 5 or 6 years ago. And I remember when Ben came in my office, one of my PhD students, and he said, "You have to read this blog post. And I think it's really, really well written. Please go ahead and read this if you don't already know it." So Andre trained a 3-layer RNN, which basically just means you have those hidden states that map into this y, and y then isn't the prediction of the network, it's basically the input to the next layer, and then this produces another output, which is the input to the next layer. And so you have this kind of stacked RNN structure, and then at the third level, you have the prediction that is then compared to these labels that we have. And he trained it on a, not that large body of Shakespeare texts. And the cool thing is that if you then run this trained network as a generative model, you see that this actually sounds like Shakespeare. So you should go ahead, read this blog post. I highly recommend this. So why have we looked at those simple RNNs? Well, because it's an introduction to RNNs, but also we wanted to have something that is better. And what means better, becomes more clear when we look at what those limitations and problems are of the original formulation. So first of all, it's a rather high memory footprint that we have. So long-term dependencies. So if we have our first symbol that has an effect on the symbol in like 100 or 300 or 3000 time steps, well, this means long-term dependencies. Yeah. So in order to model these, we have to have a rollout that is that long, at least that long. And so we have to keep all inputs, weights, and hidden activations, for example, in memory. And this is, depending on the size of the network, this is limiting really the sequence length. The second problem is the result of a thought experiment. Let's have a look at what we do in training. So let's think of a long sequence, and we propagate the gradient back through time, right? So each of these boxes here is the hidden state, and we propagate the gradient. And remember how this is done. You multiply the derivative of the activation with the weights times the derivative of the activations times the weights, right? So you multiplicatively collect all these weights. And now what happens if these weights are small, so smaller than 1, maybe close to 0? Well, the gradient vanishes, right? So in the end, you come close to the numerical precision of these numbers, and then you either have a 0 or even if you have very, very small gradients that you still can resolve in your numeric precision, you walk very slowly, right, in weight space. Okay, but then, this happens even if those weights are close to 1 but still below 1. And if they are above 1, well, then you have kind of the opposite. The multiplicative chain here leads to an explosion of the gradient. And while we can kind of handle this by clipping the gradient, there's no way or no solution really to the vanishing gradient problem. Yeah? Except something that we can do with a different architecture, and this architecture is the long short-term memory, or there's a simplified version called GRU, and we'll look at these in the second part of the lecture. I'll upload this one here, so you have something to watch and learn. See you all in the second part. Bye.